Today is day 2 talking about concurrent lines. So let's kind of refresh our memories what we talked about last time. Concurrent lines, remember that that's just 3 or more lines that meet at one point. Okay, so remember we said yesterday when 3 lines come together, where they meet, that is called a point of concurrency. Okay, so we kind of began that discussion yesterday, and remember we talked about the circumcenter and the incenter. So they're very similar, just slightly different though. So you just practiced using your contractor to construct the circumcenter and the incenter. So right now, I'm not going to use my contractor. I'm just going to draw a rough sketch because you can recognize the circumcenter by constructions and a different way. Remember that the circumcenter is the point of concurrency of the perpendicular bisectors. Okay, so we could do the fish thing on our picture here, and where those 3 bisectors meet, that's called the circumcenter. You could also do like a rough sketch. So maybe I want to cut this side in half at a right angle. So maybe something like that would be seen as a perpendicular bisector. I could do the same thing for this other side here. Maybe draw that piece in. So that would be them showing you that that side's perpendicular and it's bisecting this side. And then you could draw the third one in. And I'm kind of just eyeballing this here, people. That's a perpendicular bisector too. Okay, so you might see them like show you a picture like this, and they might say, hey, this point of concurrency right in the middle here where these lines are meeting, what's that called? Okay, so that's your circumcenter. It's where the perpendicular bisectors meet. Okay, now there's a couple things that we knew about the circumcenter. So the first was that the circumcenter is the same distance from the angles of the triangle. Now, I always kind of like remember it this way. If you bisect the sides, which that's what you're doing with the perpendicular bisectors, you're cutting the sides in half. So if you bisect the sides, you're the same distance from the angles. And you'll kind of hear me tell you guys that often because that's how I remember it. It's like the opposite. If you cut the sides in half, you're the same distance from the angles. So they're like reverse of kind of what you would think it would be. Cut the sides in half, same distance from the angles. We also talked about yesterday that the circumcenter is the center of the circumscribed circle, which that's the circle around the triangle. Okay, remember we used our contractor to draw it and we just had it touch every vertice. So it's the circle around the triangle. So that was the circumcenter, little refresher there. Remember the incenter is very similar, but instead of it being the point of concurrency of the perpendicular bisectors, it's the point of concurrency of the angle bisectors. Okay, so I'm going to draw a sketch here too, I'm eyeballing it. You could use your contractor, but I'm not going to. So if I cut all the angles in half and drew like a piece in that did that, let's see, it would look something like, see, that one's being cut in half. And they would be showing you that it's cut in half because they'd mark those 2 angles on either side congruent. Okay, so maybe that's the piece that cuts that angle in half. Now when I cut the top angle in half, let's see, that looks like it's right about down the middle. They'd mark those 2 pieces congruent to show you that that's the angle bisector. When you draw the third angle bisector in, it should meet right where the other 2 lines did. Okay, and they'd put 3 little marks on those 2 pieces to show you that they're the same. Okay, so when you cut all 3 angles in half, where those lines meet, those are concurrent lines, 3 more lines meeting, where they meet, that's called the in-center. Okay, so the reverse of the circumcenter, the in-center, is the same distance from the sides of the triangle. And so it's kind of like goes exactly along with the circumcenter. If you bisect the angles, which is what the in-center does, you're the same distance from the sides. So they're kind of reverse of each other. If you cut the angles in half, you're the same distance from the sides. Okay, and then the last thing, the in-center is the center of the inscribed circle, which is inside your triangle. So I'm going to do a rough sketch with my pencil, and I don't want to like screw it up too much. But the inscribed circle like just touches all 3 of the sides. So I did it real lightly because it's pretty hideous looking. You'd want to use your contractor to make it perfect. It'd just be right inside the triangle. And the circumcenter is the center of the triangle, or the circle that's just around your triangle here. And again, that is a hideous circle, but you get the idea. It goes around it, inscribed inside. Okay, so that was day 1. That's kind of what we talked about last time. Today, there are 2 more centers. So there's a total of 4 centers, you guys, 4 points of concurrency. Circumcenter, in-center. Those are 2. On the back, centroid, something called an orthocenter. Okay, so there's 4 centers. Those are them. So if you want to highlight those 4 terms on your paper too, couldn't hurt. Those are like the big things. Now, before we can talk about this next center, this next point of concurrency, we need to figure out what a median is. We're going to draw it in on this triangle here. A median is a segment with endpoints at a vertex and the opposite midpoint. So I'm going to draw a picture over here to kind of show you what that means. Vertex is just like one of the angles. So let's say I go from, and I'll label this A, B, and C, so we kind of all are on the same page here. Let's say I start at vertex A, or this angle. A median connects the angle to the side across from its midpoint. So I want to connect A to the midpoint of side CB. So let's just eyeball it, and we could measure, but that looks right about in the middle. We'll mark the 2 pieces congruent so we know it's in the middle. If you go from A, that vertex, to this midpoint, that's called a median. Now, realize you could draw in all 3 medians. So I could go from point B, that vertex, to the midpoint opposite or across from it. So I could draw that in, and if I go from B to that midpoint, that's a median. And you could go from C to the midpoint of AB. So if you draw that in, that's a median. So these are concurrent lines. There's 3 lines meeting at one point. Where these 3 lines, these 3 medians come together, that is called the centroid. Okay, so the centroid is the point of concurrency. It's where all of the medians meet. Added more terms to the list here. Now, the centroid, it's not like the same distance from the angles or the sides. I mean, there's nothing that really like goes along with it, like the circumcenter and the in-center. But there is one thing you want to note about it, something that makes it important. It's called the center of gravity. So what that means is if you were going to like balance a triangle like on your finger, you would put your finger on the centroid and it would like be level. We'll kind of talk about some examples of this tomorrow in class, kind of like how this is useful, but just be aware that it's called the center of gravity. Now, the centroid also does something else. So we got a little theorem here, which can be proven, but we're not going to. I can recognize that these are centroids in the center here because they've got all the medians drawn in. So like this is going from point A, the vertex, to the opposite midpoint. Point C to the opposite midpoint. Angle B to the opposite midpoint. So this is a picture of the centroid at point D. Something happens along with it being the center of gravity with the centroid. So notice that they're telling you some lengths on this picture here. They told me that DE is 6, so that's right here. They told me also that AH is 11. Okay, so AH is here, one of the sides of the triangle. We got to find all these different pieces. Now, finding, let's see, BH, that should be pretty easy because those two pieces have 3 marks on them. That means that they're congruent. So if AH is 11, BH is 11. We should also be able to find AB pretty easily. That's this whole side, 11 and 11, that'd be 22. Now it's going inside and finding parts of the median, which they want you to do with BD and BE. That's a little new to us. Now, BE is a median, like we said. The centroid, you guys, breaks up the median into like a piece that's double another piece. So for example, this piece down here, this is very obviously, so here's the centroid. It breaks it up into BD and DE. Use your common sense. DE is a lot smaller than BD. And I can just look at it and I can see that. The longer piece of the median, if you double the shorter piece, that's how long the longer piece is. So if this piece is 6, BD has got to be 12. Okay, so then if you want to find the whole thing, obviously if it's 12 and 6, I'm going to add those together and I get 18. Okay, let's use the same idea to fill in some pieces on this second example. They tell you that WM is 16. So this time that's the longer piece on the median. They tell me that WX, ooh, I just labeled the wrong piece. We're going to wipe that out, pretend that never happened. So sorry, MX is what I want to find. WM is 16. Oh no, I did label it right. I'm losing my mind. WM is 16 and RZ, okay, so this whole median is 18. That's going to be the weird part. Okay. I want to find MX. So focus on the median WX. This time, like I said before I thought I was wrong, they gave you the longer part of the median, 16. So you're going to cut that in half to get MX. So that'd be 8. If the longer part's 16 and the smaller part is 8, you just want to add those together and you get 24. Okay, so when they give you the entire median, which they did with RZ, they gave us 18, you should know that the smaller part is like one piece and the longer part is double that. So the median really kind of breaks it up into 3 parts. So if I do 18 divided by 3, I get 6. Now, one of the 6's will go for ZM. The other 2 6's are going to make up the longer part. Okay, and then that works. Like if I double 6, I get 12. The whole thing's 18. So MZ would be 6, and MR would be 12. All right, the last center we're talking about here, so we got the centroid, and then we got the orthocenter. Before we can kind of say what the orthocenter is, we need to know what an altitude is. And we've already seen this. Remember like the leg, altitude, all that good stuff? So we are familiar a little bit with what an altitude is. The formal definition, it's the perpendicular segment from a vertex to the opposite side. Okay, and they gave you pictures here. So they're talking about they go from one of the angles and they drop down a perpendicular piece to the side across from it. And we could draw all three in, and you already know kind of what that's going to lead to. But they're showing us three different examples of an altitude here, like on this first one, vertex, perpendicular segment. That one, there's the altitude, and that one, there's the altitude. So depending on what kind of triangle it is, that like positions where the altitude goes. If the triangle is acute, all the angles are less than 90, the altitude ends up being inside the triangle. If it's a right triangle, your altitude is going to be weird, but it's like right on the triangle. So it's like one of the sides. So in this case, the altitude is a side. In my obtuse triangle here, the altitude actually went outside of it. Okay, so that's kind of weird. Recognizing that will take a little bit of practice. If I looked at the acute triangle here, you could draw in all three altitudes, vertex, perpendicular across from it, vertex, perpendicular across from it. Okay, and then where those meet, that point of concurrency is called the orthocenter. And there is absolutely nothing that's special about the orthocenter. All you guys have to know is that that's where the altitudes meet. So we're just going to say point of concurrency of the altitudes.